Hello and welcome to this new lecture on Mach number relations. So in this lecture we'll try to develop expressions relating the variation of temperature, pressure and the density of an ideal gas with respect to the Mach number. So let's start first with the temperature. So from the previous lecture we said that the stagnation enthalpy H naught is equal to H plus V square over 2. And we know that for an ideal gas, the enthalpy is related to its temperature by the following, where H is equal to Cpt. So now H naught, we can replace it by Cp T naught. H is equal to Cpt plus V square over 2. Now we divide both sides by Cp, we'll have T naught equal to T plus V square over 2Cp. And also now we can divide by the temperature of the ideal gas. So we have this ratio T naught over T equal to 1 plus V square over 2 CPT. You should know from thermodynamics that the specific heat at constant pressure for an ideal gas is equal to the gas constant R multiplied by the specific heat capacity ratio K divided by K minus 1. So if we replace this expression here, we will have T naught over T is equal to 1 plus V square over 2Cp, so 2RK over K minus 1 into the temperature. Now let's rewrite this equation in a better way. So we'll have T naught over T is equal to 1 plus K minus 1 over 2 into V square over KRT. So if you look carefully at this term, this is a familiar term. In fact, when we've talked about the speed of sound in ideal gases, we said that the speed of sound C is simply equal to the square root of KRT for an ideal gas. So C square is equal to KRT. So this term is the speed of sound squared for an ideal gas. Now we have this ratio V square over C square, which is the Mach number square. So we will have T naught over T is equal to 1 plus K minus 1 over 2 into the Mach number square. So we have a relationship relating the variation of temperature for an ideal gas with respect to the Mach number. You can leave this expression as it is. However, I prefer to put the temperature in the numerator instead of the denominator, because in this way you will have the temperature will be directly proportional to the expression to the right. So let's compute the inverse of both sides. So we'll have T over T naught is equal to 1 plus K minus 1 over 2 Mach number squared to power minus 1. So now you should know from this expression that when the Mach number increases, the temperature of the ideal gas should decrease. So you can use this expression, for example, if you know the value of the Mach number, and from knowing the value of the Mach number, you can calculate the temperature for this ideal gas. So please remember that this relationship is only applicable for adiabatic flow, because we started the development of this expression from this expression here, H naught equal to H plus V square over 2, and the definition of the stagnation enthalpy is only valid for adiabatic flow. And also you can say that this expression is valid for isentropic flow, because we know that isentropic flows are simply adiabatic and reversible flows. Okay, so isentropic flows are adiabatic flow, but you cannot say the inverse, that that all adiabatic flows are isentropic. So to make this short, this equation is applicable for adiabatic flows and also for isentropic flows. Now let's see the variation of a pressure with respect to Mach number. From the previous lecture, we have developed a relationship relating the pressure ratio to the temperature ratio for isentropic flow. So we said that P naught over P is equal to T naught over T to power K over K minus 1. So we have obtained this expression by first starting with the assumption that we have isentropic flow. So the pressure equation that we will obtain now, function of the Mach number, will be only valid for isentropic flow. Okay, so let's also here compute the inverse. So to put the pressure in the numerator instead, we will have P over P naught instead is equal to T over T naught to power K over K minus 1. So now we will replace T over T naught by this term in the right side of the equation. So we'll have P over P naught is equal 1 plus K minus 1 over 2 into the Mach number squared to power minus 1. So to power minus 1 to power K over K minus 1, it will be to power minus K over K minus 1. So this is an expression relating the pressure variation of the ideal gas with respect to the Mach number. And of course here we have the same conclusion that when the Mach number increases, the pressure of the ideal gas will decrease. And also please remember that this equality is only valid for isentropic flow of ideal gases, not adiabatic, isentropic. Okay, because as we said, we've started from this expression here, and we have derived this relationship between the pressure and the temperature variation by starting with P over rho to power K is equal to constant. So if you don't remember this, please go ahead and review the previous lecture. Okay, so when n is equal to k, we said that we have isentropic flow. So this equality is only valid for isentropic flow of ideal gases. Now let's do the same for the density. Also we said that rho over rho naught is related to the temperature T over T naught to power 1 over K minus 1. So replacing T over T naught by this Mach number expression, we have a relationship between the variation of the density and the Mach number. So we'll have rho over rho naught is equal to 1 plus K minus 1 over 2 into the Mach number squared to power minus 1 to power 1 over K minus 1, it will be minus 1 over K minus 1. So this is another relationship relating the variation of the density of an ideal gas with respect to the Mach number. And here we have the same conclusion, that when the Mach number increases, the density of the ideal gas should decrease. Okay, because simply because all the powers here are negative. So this is an inversely proportional relationship between the properties of the ideal gas and the Mach number. And please also pay attention that this density expression is only valid for isentropic flow of ideal gases. Now there is a special condition when the ideal gas reaches a Mach number equal to 1. The properties of the ideal gas will be called the critical properties. So this is a special condition. We call it the sonic condition. So at sonic conditions, meaning when the Mach number equal to 1, the properties of the fluid will be called a critical properties. And to distinguish critical properties from properties at other conditions, for the critical properties we use a superscript next to the properties. So we'll put this asterisk, or we call it a star. Now let's evaluate the critical properties at the Mach number equal to 1. So for the temperature we will have T star divided by T naught. So next to the temperature, when you see this star, it means that this temperature is evaluated at Mach equal to 1. So simply in the expression of T over T naught here, you replace the Mach square by 1 square. So you will have 1 plus K minus 1 over 2 into multiplied by 1 squared to power minus 1. So this will be equal to K plus 1 over 2 to power minus 1. Now, for example, for air, the specific heat capacity ratio K will be equal to 1.4. So for air, T star over T naught will be equal to 2.4 over 2 to power minus 1. So this will be 0.8333. Now also for the pressure, at the critical condition, P star over P naught will be equal to, similarly, K plus 1 over 2. However, the power here will change, will be minus K over K minus 1. And for air, meaning for K equal to 1.4, P star over P naught will be equal to 2.4 over 2 to power minus 1.4 over 0.4. So this will be 0.5283. And similarly, for the density, we have rho star over rho naught. It will be K plus 1 over 2 to power minus 1 over K minus 1. And for air, this ratio will be equal to 2.4 over 2 to power minus 1 over 0.4. So this will be 0.6339. So these are the properties for an ideal gas evaluated at the sonic condition, or what we call them the critical properties. Now, what we want to do next, I will show you, I will draw the curves or the graph showing the variation of the properties of ideal gas with respect to increasing Mach number. So let's see how to do this. So let's draw. In the y-axis, we'll have the properties, and in the x-axis, we will have the Mach number. So here, we're starting at Mach number equal to 0. We have Mach number 1, for example, 2, 3, 4, 5. And let's examine the relationships and try to compare them. So between the square brackets, you can notice that for all the properties, we have the same expression, which is 1 plus K minus 1 over 2 into the Mach number square. However, the main difference is in this power here. For the temperature, we have to the power minus 1. For the pressure, we have minus K over K minus 1. And for the density, we have minus 1 over K minus 1. So if we want to compare the powers as absolute values, because all these powers are negative quantities. So if we want to compare them as absolute values, the temperature has the smallest value of power, followed by the density, and the largest value in absolute value corresponds to the pressure variation. So we expect that okay, for all the properties, the trend will be a decreasing trend for all the curves. However, we will expect that the temperature will exhibit the slowest or the slowest decrease in temperature with respect to the Mach, with respect to increasing Mach number, and this will be followed by the density variation, and the fastest decrease in pressure with respect to the Mach number, since the pressure has the highest power as absolute value. So if you want to draw these curves, so at Mach number equal to 0, we have stagnation properties. So the ratio rho over rho 0, P over P0, T over T0 will be equal to 1. And let's say here we have the mid distance 0.5. And we start with the temperature curve. So at Mach number equal to 1, for example, for air, we have 0.8333. So at Mach number equal to 1, we have here approximately 0.8333. So this is the curve for the temperature, which, as we said, the temperature will have the slowest decrease in its value with respect to increasing Mach number. Then this will be followed by the density. So at Mach equal to 1, we have a value of rho star over rho naught equal to 0.6339. So the density also will be decreasing. So this is rho over rho naught. And the fastest decrease will correspond to the pressure variation. So at Mach equal to 1, we have 0.5283, and this is the pressure decrease. So this is P over P naught. So this is the three curves, T over T0, rho over rho 0, and P over P0 for increasing Mach number. Now, you can use these relationships. For example, if you know the value of the Mach number, and you can calculate, for example, all the properties, the temperature, the pressure, and the density, by simply substituting the value of the Mach number. However, let's say you have the opposite problem. Let's say you know the property, the temperature, for example, and you need to find the Mach number. So you need to do some extra manipulation on this equation to solve for the Mach number given the properties. However, what I prefer to do is to use tables. So if we go to this compressible flow tables.pdf, which is, I provided this table for you in the last section of this course. So if you go to the last section of this course and you download the exercise files, you will see the compressible flow tables.pdf. And let's look into table B1. So in this table, you have 5 columns. So a column for the Mach number, another one for the ratio of pressure, the third one for the ratio of the density, the fourth one is the ratio of the temperature, and the last one is the ratio of area, A over A star, which we will talk about later on in this course. So don't worry about the last column for now. And you can see that we have for several values of Mach number. So simply, how did we construct this table? We've used the equation that we've derived now in this lecture, and we substitute for several values of Mach number, and we find the corresponding value of all the properties. And if you scroll down, you can see that you will have values up to Mach number equal to 5. So you can use this table up to Mach number equal to 5, and it is very easy to use this table. Simply, for example, if you know what is the value of the Mach number, so you search in column 1 and you can read the properties that you want to find. And you can do also the inverse. For example, if you know the properties T over T naught, rho over rho naught, P over P naught, you can also use the table and find the corresponding Mach number. And also, if, for example, let's say you did not find exactly your value in this table. Let's say you have a Mach number equal to 0.042. So this is as a value is not present in this table. So you simply do a linear interpolation on the properties, and we will see how to do this later on when we solve a problem. So you can either use the equations directly to solve, or you can use these compressible flow tables. So what I will do in this course, I prefer to use the tables to solve problems. Okay. Now in the next lecture, we will solve problems. So we need to apply what we've learned so far. So we want to practice using these concepts and using the tables. So let's see how to do this in the next lecture.